All right. Hello, everybody. Thanks for coming to this talk. My name is Ning Shi. Today, I will talk about real-world anti-fraud using an in-memory processing engine. Excuse me. So some of companies or people may refer to this problem as fraud detection. I'm calling it anti-fraud here for a reason, which I'll go into during the talk to let you know why it's not just detection, but there's another piece that's more important than it. So let's start. A little bit background about myself. I'm the director of engineering at Volta EB. We are an in-memory database company located in Bedford, Massachusetts. We've been around for about 7-8 years. I've been with the company since the beginning, so I know a lot about the database. I've worked on pretty much all aspects of the database. This is my email address. If you have further questions after the talk, feel free to reach out to me. During this talk, I will first start with the problem. What is the fraudulent activities, why it's important and challenging, and then I'll cover why Volta EB is a good fit to this problem, to solve this problem, and then go into a little bit of the technical details to describe the architecture that we see in production today, and hopefully that resonates with some of your challenges that you are seeing. So to start off, fraudulent activities. As a simple example, we all use credit card. So when you swipe a credit card on the POS machine, your request goes through various networks, and eventually it goes to the card issuing company, the bank, which has to provide authorization to your credit card request. And then after either accepting or rejecting, it sends the response back to the POS machine, and then the merchant will either accept or reject your transaction. So this is the simplest case, where you are actually using your card and it gets accepted. However, sometimes the card could be stolen, or that the card information could be leaked to fraudulent users, and they will try to use your card to steal your money. So in that case, transactions could come from various places. Could it be online purchasing different things, or it could be from different locations using different POS machines. And these bad transactions will also go to the issuing bank. And from the issuing bank perspective, it's kind of hard to tell which ones are good and which ones are bad. So that's the challenging part, is to determine which ones are legitimate transactions and accept those and reject all the others. This is the ideal case where all the bad transactions are being rejected and only the good ones are being accepted. That's the simple problem that we're facing today. Imagine that you have millions of credit card users using your card 24/7. So there are a lot of transactions coming in that needs to be determined whether it's good or bad. And it's not just limited to credit card. It could happen to account hacking. For example, somebody tries to brute force guessing your password, trying to log into your account. It could be your Apple account or Google account. So those are all fraudulent activities that could cause damage to persons or companies. And it could be online bots. For example, like advertisements. You could have bots trying to hit ads and make money out of that way. Or in a loose sense, I think DDoS, which is denial of service, is also sort of in this and fraudulent activities bucket, because it's also some bad activities trying to, in this case, it's not trying to gain access to certain resource, but it's trying to cause the service to be unavailable to good users. So in a loose sense, I think it's also in this category. There are a lot of other examples, but these are just some ones that are more common today. And now start with fraud, anti-fraud. I try to summarize it using one sentence, and I think this sentence captures the anti-fraud solution pretty well. The goal is to identify and protect the user from fraudulent online activities by using the means of patterns. So there are three keywords here that I would like to highlight. First is identify, and then protect. The last one is patterns. The reason I think these keywords are important is because, first of all, what you're doing as the bank, for example, is to leverage your historical and real-time data to generate patterns, to find out patterns of fraudulent activities. Once you figure out those patterns, you want to apply those patterns to identify or classify those events that are coming in at real time. And then eventually your goal is to protect the users. So you want to react to these events at real time, make your decision on each transaction. Based on these three keywords, I sort of categorized anti-fraud into these bullets. These are all the characteristics of any anti-fraud solution. Your number one goal is to stop fraudulent online activities, because there is always a money tag associated with fraud activities. In the credit card fraud example, if you have a false positive, meaning that it's a legitimate transaction, or it's actually a bad transaction, but you didn't catch it, you let it through, meaning that somebody has to cover that cost. So there's a money tag. But if it's a false negative, meaning that it's a legitimate transaction, but you identified it as a fraudulent transaction, then you may lose a customer. So either way, you're losing money. So being accurate is really important here. And the second point is that it affects all activities. Before looking at the activities, you can't just say, I want to apply certain rules to only the bad ones or the good ones, because you don't know which ones are good or bad. You have to apply all the rules to all transactions to find out which ones are good or bad. The third point here is that end users actually feel the impact. In the credit card example, if you do too much during the transaction, then the user may be waiting for too long and lose interest or lose patience, right? And there's a trend now in the industry to actually move from post-transaction detection to in-transaction prevention. That is the main reason that I use anti-fraud and not the word fraud detection in this talk, because prevention is the ultimate goal. It's not just detecting it afterwards. You want to catch it as it happens and stop it from happening in the first place. And after, the last point, but not the least, is fraud activities actually change over time. As the banks getting more smarter to detect these fraudulent activities, people are finding out new ways to trick people or trick the banks into thinking that there are good transactions. So it's very important that the solution also have to evolve along with the fraudulent activities. And all of these bullet points can be sort of categorized into three things, I think. Like the first 2 points, it means that the solution, whatever it may be, has to be accurate, because it has a money tag associated with, no matter whether it's false positive or false negative. So you want to be as accurate as possible. And then the middle 3 points says that the solution has to be fast, because the end user actually feel the impact. You want to lower the impact on the end user to make them happy. It's sort of the quality of service that you're providing. And then the last point means that it's evolving, because the fraud activities are evolving. Your solution has to be evolving. So based on these 3 points, accurate, fast, and evolving, I think the Volta EB is a pretty good solution for this problem, and I'll go into the feature set that Volta EB provides and explain why it matches what a good anti-fraud solution requires. So these are sort of the points that Volta EB offers today, and I'll break them down into those 3 categories and see how they match. Number 1 is quality of service. In a database or in a system, when you look at quality of service, usually it's response time, meaning that you don't want to take too long to do certain things. Otherwise, your end user or your application could be waiting for too long. So the low response time translates to quality of service in this case. And when I say low response time, I'm talking about like 0.1 0.05 second. That's 50 millisecond response time for a transaction. And in Volta EB, a transaction is actually a complex transaction that could involve multiple SQL statements. It's not a single query. And number two, throughput. That goes hand in hand with your size of your business. As you scale your business, you may get more transactions, business transactions. So you would like your system to be able to scale out and be able to handle concurrent workload. So high throughput is also important, which is the other point that Volta EB is really good at. We're very good at high throughput, low latency workload. And number three, transactions. Volta EB offers transactions as ACID, durable atomic transactions in the database, so you can have you don't have to worry about transactions failing in the middle or eventual consistency. And you can change your rules online without having to take the system offline for maintenance. You can always apply the rule changes to the database, and it will automatically pick up the new rules and apply those to new transactions. And Volta EB uses SQL because it's a relational database. We use SQL to access your data. And it's highly available because it's a clustered database. So if a single machine fails in a K-safe cluster, you always have a different replica to handle that same piece of data on a different machine. And it's also scalable, meaning that you can add more machines to expand the capacity and both the throughput and the storage capacity of the cluster, so you can always scale out as your business grows. Remember the previous slide, I talked about 3 different key points that the anti-fraud solutions are looking for. So here in Volta EB, the low response time and high throughput maps to the fast requirement. And number 2, since we provide transactions, ACID transactions, you can express your logic inside the transaction. It makes them accurate. And then since the fraudulent activities are evolving, you would like your database to also evolve as it goes. So online rule changes gives you that your power to actually change your rules as the fraud activities are changing. In fact, in production, we've seen customers changing rules every hour or even more frequent than that as they discover new rules that can be applied to detect fraudulent activities. So they can change the rules as often as they want, and it will be applied instantly to the production system. So with these combination, Volta EB really makes some of the impossible use cases now possible to do. So one of our customers actually couldn't do in-transaction prevention before, but now after switching to Volta EB, it's not just lowering that response time to do better detection, but now they can actually move into in-transaction prevention. It's a totally different category for them because now they're not catching things afterwards. It's not after the effect. They're catching them as they happen. So some background of Volta EB as the company and the product. The company was founded by one of the database researchers, Michael Stonebreaker, who's a professor at the MIT, and some of you may be familiar with him. He won the Turing Award in 2014, and he's founded many different other companies, including Vertica, Streambase, Tamer, and he also started Postgres back then. So he's a well-known database researcher. He started Volta EB as a next-generation transaction processing system. And here we are today doing exactly that. So Volta EB as the product, we're open source on GitHub. In fact, we've recently made some changes to our product to make it, the open source version more competitive. So if you go to our website, you can see what features we have in the open source edition right now. We have durability in there with snapshots, and it's fully case-safe, meaning that you can have many replicas of the same data on different machines. Machine failures will not take down the database, and you can import data from message queues such as Kafka or other message queues and export things down to your downstream data lake or analytics system. All of these are in the open source edition, so you can just try it out and see the code for yourself. And we also have enterprise edition that has a little bit more feature to enterprise use cases, such as database replication is a big feature in the enterprise edition. And Volta EB is fully scalable. We use active replication between the replicas, meaning that you'll always have a consistent picture in the database. You will never see a certain replicas ahead or behind the other replicas in the database. It's strongly consistent. And we support ACID serializable transactions, and we can do millions and millions of those in a single second. And the database is in memory, but we persist everything onto disk. In case the whole cluster or your data center goes offline, you can recover from that. So you don't have to worry about your data going away if you lose power. And we have different modes for disk persistence, both asynchronous and synchronous. And the average latency is usually under 1 millisecond, so in the microsecond range. But what we look at most of the time, and I will focus on in this talk, is the 99th percentile latency. Because to these types of use cases, such as fraud, anti-fraud, the average doesn't really mean much to these use cases. It's the predictability of your low response time that really matters. You can't just say, yeah, the average is good, but then the 99th percentile goes, way up to like hundreds of milliseconds. Then it's less interesting for them. They can't live with 20 or 30% of the business transactions going way beyond their threshold. They have to be able to guarantee that 99% of the transaction will be lower than certain latency. That gives them the confidence that their quality of service is good. So we focus on the 99th percentile latency more so than the average latency here. And for the 99th percentile, a lot of the anti-fraud use case that we see are under 50 milliseconds within the Volta EB cluster. So that's the end-to-end latency response time. And a lot of our customers use terabytes of data in production with replication. So with a cluster of machines, each has hundreds of gigabytes of memory on each server. So being in memory itself doesn't really give us a lot of speed, and that's not scalable as you go beyond just certain throughput. So what we've done in the past is that we've designed the whole architecture from ground up and coming up with a totally new design to address these performance requirements that actually makes the database really fast. So the number one thing is that we used a totally no-wait design in the database. So the whole architecture, we assume that we don't want to wait on users or any external database transactions because those are slow. Waiting on external things, meaning that there are many networked round trips, and you have to then wait on the application to make a decision on whether this transaction commits or not. So that's a lot of time wasted on those things, which means that we actually do server-side transactions in Volta EB. And all of your transaction logic actually runs with the data on the server itself. So instead of moving the data to your transaction, to your business logic, we're actually moving the business logic to your data. So you don't have to copy a lot of data back and forth to make a decision, which means sometimes a lot of those data may be wasted if you don't need them. The second point is to maximize parallelism. We use the trick to partition your data across the cluster nodes. And in fact, we are not just partitioning across different nodes. We're actually partitioning across different CPU cores. Because now each single machine has so many different CPU cores, we want to leverage all of the processing power of those cores. So we went a little bit beyond that to say not just by node, but we are actually just looking at each CPU core, and we don't care whether this CPU core collocates with another CPU core or not. So we're just looking at the smallest unit that we're looking at is CPU cores, and each partition is bounded to a CPU core in the database. And we don't use shared memory to handle concurrency. We actually handle concurrency by scheduling, because each partition is a single threaded of execution that guarantees your transactions are serializable, and it also means there's no context switches or shared memory access. It's always local to that partition. And the last point is that the data model and the storage that we've built actually maximizes the speed of your memory. First, we have real-time materialized views. A lot of you may be familiar with materialized views in relational databases, like the traditional ones, meaning that it's just a cache of the result set. In Volta EB, it's not just that. We're actually updating the materialized view for you at real time. As you change the underlying table, the view gets updated. So the cost of updating the materialized view is actually amortized across all the mutations to the table. As you insert a single tuple, the view gets updated. As you delete it, the view gets updated. So it's always up to date whenever you look at the view. And second, we have smart indexes that actually support some queries that are optimized for Volta EB, such as ranking queries, meaning that you could, given certain criteria, you know exactly how many things are lower or higher than certain points without actually going down the subtree to count them, because we actually record the number of things that are under certain subtrees, so you can quickly answer those kind of queries. And we now support expressions and functions in primary key index or secondary index in the database. You can also define a filtered index by using a where clause in your index definition. So you can have a sparse index that doesn't take up much memory if you are only interested in certain subset of your table data. And we store all of your data compactly in memory, and using lazy deserialization, we don't waste computing power to deserialize data if it's not needed at the end. Typically, people use Volta EB in this type of architecture where the data is streaming in, and Volta EB is actually sitting at the very front of your business. Data or requests are streaming into the database at a very high rate, and Volta EB takes all those requests, makes decision to do real-time analytics on it, and then make the decision. Either the decision will go back all the way to the issuing client, or you can save the decision to a downstream data warehouse for long-term storage. So next, I'll look at an architecture that solves the anti-fraud example and sort of highlight why this architecture works for that example and some of the points that are very interesting. So the way I think of it is that anti-fraud is actually a typical fast data pipeline problem. There's a fast data piece where you have a lot of real-time transactions coming in that needs to be handled. Unlike detection, you can do it after the effect. So it might not matter that much if you handle all the transactions right away. For the prevention piece, the transaction prevention piece, you do want to handle each single transaction right away, so as fast as you can. In this case, the fast data piece is the piece that handles all those real-time transactions. So to your left, there could be a message queue. It could be your own Java application or application written in any language that actually takes all those credit card transactions and sends them to your application server. And the application server then talks to Volta EB using VoltDB's transaction to make the decision on whether this credit card transaction is a fraud or not. And then the decision may go back to your issuing client, and then you'll get the final response of acceptance or rejection. In this chart, I'm showing two pieces. The upper piece here is showing one data center, and then the lower piece is actually a complete replica of the part that's above it. So you can have two exactly same databases running in two different data centers for disaster recovery. VoltDB has disaster recovery built into the database, meaning that the two databases will automatically asynchronously sync with each other so that transactions are always written to your replica in case the master cluster, the whole cluster goes down and you cannot recover it immediately. You always have a hot backup somewhere else. And normally, if your master is running well, then the application will be talking to your master database because that's where the data can be written to. Otherwise, the replica is just a read-only database waiting to be promoted to be the master. Once the decision is made and gets sent back to the issuing client, you can also decide to send all the decisions as well as the transaction request to a data warehouse for long-term storage. So VoltDB can do that automatically for you using different export connectors. We support exporting to HDFS, to Kafka, to various other systems. Could also be a relational database like Vertica. And typically now people use Spark to do a lot of machine learning on historical data to figure out patterns, since this use case relies a lot on finding out those patterns. Once Spark runs a machine learning job on those historical data and figure out that new parameters needs to be updated to better catch those patterns, then it needs to be fed back into your real-time operational database so that new events can be classified using the new parameters. That can be done using a bulk load process that we support. You can use our bulk loader. We have bulk loaders supporting different ways of loading data into VoltDB that gets all those updated information from your data warehouse back into VoltDB at real time. Once they're loaded in there, then any new transactions that come into VoltDB will be using the new parameters. So you get a more accurate detection and prevention at real time. And as I was talking about, the rules also changes. Machine learning gives you new parameters, new values for the parameters that you plug into your algorithm. But the algorithms themselves have to be written by people because people understand the problem. You will never have machine write a whole algorithm for you because you don't even understand what it's trying to do. So rules are typically written by people, and those rules, once written and tested, they need to be added into your production database. So we also support online rule changes using either your terminal window, or we have a web interface for changing your business logic in the database at runtime. And that change happens instantly as you submit them, and the next transaction that runs after that will be using the new business logic. So there were two things that I would like to highlight here. Rules, meaning the rule set that people use to detect fraudulent activities, they are actually written and defined in VoltDB stored procedures. In VoltDB, a transaction is a stored procedure that's written in Java, and you can within that you can use SQL to access your data. So since it's Java, you can use any Java library that you like to write complex business logic, and it's very flexible. And you can have tens or hundreds of SQL statements within a single stored procedure. When the stored procedure runs, it runs as a whole atomic transaction. You don't have to worry about the transactions failing in the middle, or when a server fails, what happens to the transaction. It's all taken care of by the database itself. And as I was talking about, we have instant rule set changes. It's actually store procedure updates inside Volta EB. So whenever you change your rule set, you can just update that store procedure logic in the database. It happens instantly without any delay. Next is accurate in-transaction prevention. And the transaction I'm talking about here is the business transaction, meaning that the credit card transaction comes in without letting the transaction go through on the POS machine. You can make all these decisions using this architecture. You can make all the decisions in the database, log it, and then respond back to the POS machine within a very short amount of time. So people typically don't feel that they're waiting for long, and then they will get an accurate decision back from the bank. And this solution combines the historical and real-time data together to make that decision. As we saw, Spark can run the machine learning algorithm on the historical data for you to figure out the patterns that's been happening in the past year or even longer than that. But things are also happening at real time. What about the things that happen in the past minute, past hour, past day, or past 30 days? Those are all captured inside Volta EB, and you can have your real-time analytics query to capture those. By combining the two together, you get a full picture of what fraud activities look like and what new patterns are evolving, so you can better make a decision. And server-side database transaction and predictable low response time really makes it a compelling solution. It changes the detection, which is after the effect, to in-transaction prevention. So that is what I think the biggest thing that Volta EB brings to this type of problem. We're really not just lowering the response time a little bit further, but we're actually making it predictable and low enough so that it can do a completely different solution to your business. In summary, I think these 3 points are what I think are the takeaways from this talk. First, quality of service, which is predictable low response time, is key to this type of use cases. There are other use cases similar to this that really requires low predictable response time. A lot of them are like telco, telecommunication industry, and the banking industry, the financial services. We'll see a lot of these use cases. And then accuracy actually matters because as I was talking about, having a false positive or a false negative both have consequences. Somebody has to lose money or pay for that cost. So being accurate is really, it actually translates to money to the business. So server-side database transaction makes this possible. And last but not least, high throughput is a must-have, but just having the high throughput doesn't really give you everything. You really need all of these features together to have a compelling solution to this type of problem. All right, that's all I have for today, and that's my Twitter handle and the Volta EB's Twitter handle. If you have any further questions for me, feel free to ask now or after the talk. I'll be hanging around here. And we also have a Slack channel that's active. So if you have a question for using the product, feel free to hang around in the Slack channel. We have a lot of developers there answering your questions. Any questions? Yep.
What causes the stored procedures to fire?
So the question is, what causes the stored procedures to fire? The stored procedures are written in Java as a single object. You can use any utility classes you want. So requests come in the fashion of given a stored procedure name and all the parameters that you want to pass to it. So it's just like a function call. So upstream, you're invoking. It's like a remote RPC procedure call, right?
So, but you decide when you're going to invoke the rule checker or the fraud rule checker, and is that done on every transaction, or?
That is done. So the question is, are the rules applying to all of the transactions, or just a subset of the transactions? As I was pointing out in earlier slides, you actually cannot tell which ones are bad or good, so you have to apply all the rules to all transactions at all time, meaning that each transaction each credit card transaction comes in will run the same set of rules in the database in order to know whether it's good or bad. So for example, in production, a stored procedure may be the ones that actually record the credit card transaction, and within that database transaction, the stored procedure that actually stores the credit card transaction, you run all the rules before you store it to also make the decision. So that as each credit card transaction comes in and wants to be stored in the database, you also run the rules as part of this, stored procedure. Any other questions?
Last question. So do you have gateways to traditional databases? Meaning, when businesses use Volta EB for in-memory or fraud detection, so they may have the transaction data sitting in IMC or some other databases. Do you have a gateway that connects Volta EB to those databases?
To retrieve data or?
To read the data.
I see.
Sitting on traditional databases.
So let me see if I understand the question correctly. The question is whether Volta EB has a gateway to actually access traditional databases in case the source of the data is actually in a remote database. Do we have a gateway to read those data into Volta EB and then leverage that? No, we don't, for various reasons. First, reading from a remote database may be slow. So inside a stored procedure, we don't allow stored procedures to do any I/O. Any type of I/O is disallowed. So you don't do disk access or network access. It's always just memory data access within stored procedures, so that we don't have to worry about the stored procedure taking a long time. That goes against the predictability of your low response time, right? Each store procedure is just a pure logic that accesses your data within the database. And the other thing is that for example, the credit card transaction comes in, it's at a very high rate, so the throughput is very high. It requires low response time. You don't typically write it to a traditional database and then have Volta EB look at that, because the traditional database may not be able to handle that kind of workload. What we are seeing as Volta EB is actually most of the time sitting at the front, handling all the high throughput ingestion. And then we can clean the data, dedupe the data, and then have the low throughput data going to the downstream data warehouse. It's actually sitting at the front.
What about rules that cover more than one transaction? So if somebody tries to use the same credit card at the same time from two different locations that are inconsistent, that would be two transactions that will both need to apply the rule and connect with each other in some way. So when you have that kind of rules, which are not transaction versus the state of the system, but transaction versus transaction, how do you manage that kind of rules in this database?
So the question is, what if a rule actually looks at two transactions versus just the context of a single transaction? What if you have the same credit card being swiped at the same time at two different places, and they form two business transactions that come into the database, and a rule says I want to look at both of them together to make a decision? So in Volta EB, each database transaction is, all of the transactions are actually serialized. So as I was saying, each partition is a single threaded of execution. When transactions come in, for example, the two credit card transactions happening at the same time, at wall clock time, they may look like they are happening at the same time, but they will get sent to the database and then get serialized in some fashion. One of them is going to be before the other. Doesn't matter which one. And then the one before, the one that comes first, is going to be a Volta EB transaction that goes into the database, look at all the current context and historical context, makes a decision, respond to the client, and then we're going to handle the next business transaction, the next credit card swipe. As the second one comes in, it will already have the context of the first one. So you will always see what just happened. We're not eventually consistent. What's just happened and written to the database is fully available to the next transaction. So you'll always get the up-to-date picture of what's happening. In that case, if you, since you've accepted the first transaction, maybe you want to reject the second one because that's not possible for the same credit card to be swiped at the same time at 2 different places, right? Did I answer your question?
I have more, but I'll take that offline.
Okay. I think we still have some time, so if you have questions, feel free to ask right now. Yep.
Could you talk a little bit about your clustering schemes? I mean, you talked about the Volta EB cluster, and you had shown a master and a replica, but I'm assuming the master is a multiple node cluster. That's
correct. So the question is, how does Volta EB form a cluster? In this picture here, I'm just showing Volta EB master as a single unit, and then the replica as another unit. But actually, within the let's say the master cluster, it's actually multiple nodes, multiple servers. It's not a single node. Volta EB is a clustered database with case safety, meaning that you can have multiple replicas of the same data on different machines, so that machine failures doesn't take down the whole cluster. It could be, single-digit number of servers that could handle tens or hundreds of thousands of transactions per second, or depending on your use case, it could be, 10 or 20 servers within a single cluster. But to the application, it doesn't matter how many nodes there are in the database. It's always a single database to the outside world. So the application developer or the clients don't have to worry about where data lives or how data gets distributed. All those are taken care of within the database. You can connect to any node in the cluster to access any data. And we also support distributed transactions. So for example, if you want to look at the global picture versus just a single item, for example, if it's not just a single credit card's information, then what you want to look at is the global picture of how many credit card swipes happened within the past second or 30 seconds. We also support that kind of transaction that's globally distributed within the cluster. And you get the same guarantee of being strongly consistent, atomic, and everything. So it doesn't matter whether it's single partition or distributed transaction. We give you the same kind of guarantee. Any other questions? No, actually. When we started, we were using timestamps, but we figured that it was not a good way for a clustered database on commodity servers because timestamps are not so reliable. Clocks could go backwards or forward. Skews are very hard to deal with. And so we changed the transaction management scheme to use a master-slave sort of mechanism. So for example, for a given partition, when a transaction comes in, always goes to the master partition. And the master partition does all the serialization and then forwards the requests, the ordered requests to the replicas. The replicas are just simply following the what the master decides. We're definitely CP, so the question is, in the cap theorem, what is Volta EB picking? We're strongly consistent, so we believes in consistency that really matters to application, and we are network partition. We detect network partition, and we favor consistency in that case, meaning that if your cluster splits in two halves, equal halves, then we guarantee that consistency is maintained within the database by shutting down one half we're not going to let two halves to continue on and resolve any conflicts afterwards. The question is there any master-slave relationship within the cluster? No, all of the nodes are shared nothing, and there's no special node within the cluster. But as I was talking, we use sort of like a master replica scheme for each partition to just determine the kind of ordering of transactions. But if the master partition goes away, a replica will be promoted to be the master. It's just simply for ordering purpose. But there's nothing special about any node in the cluster. They're all equal to each other.
Do you support auto-generated keys?
Do we support auto-generated keys? No, we don't. I assume that what you're talking is like auto-incrementing numbers. We don't support that right now out of the box, but you can simply write a stored procedure to do that easily in the database.
Do you support drivers for all the languages like Java, C?
Do we support all languages in the database? So for stored procedures, which are actually running on the servers, we only support Java for now, and you use SQL to access your data. You use Java to write your business logic. But for your client applications, meaning that those components, the green boxes that are talking to VoltDB, those can be written in any language you like. We have a lot of libraries in different languages like Java, C++, Node.js, Go, C#, Python. So for client applications, we support a lot of different languages.
Do you persist in disk as well, right? If you want to change like a simple MySQL database, the VoltDB, what are the things which I need to consider?
Yes, so for your first question, we do persist to disk because we are an in-memory database. We worry about, losing power, so that we actually persist all of your data to disk using snapshots and command logging, write-ahead logs. The combination of these two gives us the persistence to disk. It could be synchronous, meaning that you don't lose a single transaction, or it could be asynchronous if your application doesn't require, it doesn't have such a high requirement. And the second question, if I understand correctly, is what if you're moving from a traditional database like MySQL to VoltDB? What you have to consider, is that correct? So for that question, I think there are different aspects. First of all, the stored procedures, for example, now we only support Java. Even though that we use SQL to access your data, if you have a lot of traditional database stored procedures written in SQL that you want to migrate to VoltDB, those have to be written in Java. But for your data access, if it's just simple queries or insert, delete, or update operations, then those can be simply moved to VoltDB without much work. But if you have complex queries or transactions that you wrote in stored procedures in other databases, then those have to be translated into VoltDB's Java stored procedures. And the other thing is traditional databases typically don't give you a clustered or partitioned nature, but VoltDB is a clustered database from the ground up. And that means you have to think about your data partitioning, data access to actually leverage and fully exploit the performance that VoltDB gives you.
If you have time for just one last question.
Yeah, sure.
You mentioned something about bulk load for Antifraud direct. What is that used for? The data interface?
So the question is, what is this bulk loading phase that I was talking about mean? Bulk loading is, here it just means that you have something that's in this example, you have something written in your HDFS that a lot of data written in HDFS that you want to load into the database in a very fast fashion. You don't really need the transactionality of it. You just have a bunch of data you want to move into VoltDB so that you can use them immediately. So we have bulk loader that, for example, we have a bulk loader that reads your CSV file. If you want to load that into your database in a very fast fashion, we just batches up a lot of rows together and send a single transaction that could insert 1,000 or 10,000 rows at once, and then it just goes through your CSV files quickly to load the data into the database in a very short amount of time. And we also have bulk loader loading from Kafka, from other sources. The bulk loading really just means that you want a big chunk of data that gets loaded into Volta EB in a very short amount of time. So if you don't really care about the transactionality of those, then bulk loader is a good tool to use. All right, thank you very much for coming today. Hope you enjoy the lunch.